Let me set up the recording for those others. Okay, then let us start. So what are we going to cover in this class? Not a lot. You guys are going to understand what algorithm efficiency is. We are going to ask ourselves, so why time and space complexity? Why do time and space complexity matters? Okay, you might actually miss that, but go straight to time complexity, space complexity, the big O notation, so on and so forth. So let us begin, shall we? The first thing is algorithm efficiency. Obviously, we need to understand what algorithm efficiency is before we cover time and space complexity and why we use them, so on and so forth. Now, when we write algorithms, we do really care about how they perform. You basically don't want to write a program that will take 100 years to finish. You want a program that they can compile, can run, be debugged all within a few moments without really worrying. And that's why we really care about algorithm efficiency. And as we have said, we are going to cover the two of them, time complexity and space complexity. And why do you use this one? So for time complexity, you want to understand how long an algorithm takes to run, and space complexity is how much memory the algorithm uses. As you can guess, that's obvious. It's in the name. Time is obviously for how long it will take, and space is how much space it takes. And as programmers, we need to understand how to write programs so they can take the least amount of time, or they can have the lowest level time complexity and take the minimum amount of space possible to run. That's why you make fast apps, fast websites, fast everything is by understanding how these work. So I won't go too much into depth. These are not too these are not too how could I say this, used a lot. Like you see most of the people just write algorithms for the sake of it. But if you really want to be among the best in the field, you need to understand these two concepts. And I believe you can start with the first one, right? Oh, first of all, let's understand obvious. Why do time and space complexity matter? Now, efficient algorithms do save resources. That is something you have to, you can even guess out of your head. If you have something is efficient, it saves out of resources. And algorithms, efficient ones, they save resources from the computer resources to your own time, which is also a resource. So it saves a lot. And they are important now when working with large data sets and building applications that need to be fast or lightweight. That's why I said at the moment you might not encounter time and space complexity as much because you're just working with maybe a few bits of data here and there, working on your resume and all that. And applications they are building don't really care too much to be lightning fast. These are things you'll just have to slowly learn, understand, and master, so that now when you're working in the big companies and all that, you can be able to now, when you're working with large data sets, when you need the websites to be fast and lightweight, now is when you're going to implement and have to really understand these two complexities. Now, understanding them will help you choose the right algorithm for the next task. If you remember, we said algorithm is just how the steps to do a task. That is it. And sometimes, obviously, as you can guess, when you're doing a steps to do something, there are obviously easier and faster ways to do this. Like, for example, you can't just, the triangle, how it is. You can move through the right angle sides quite easily. It is longer, but you can move along there. But moving on the diagonal is obviously faster. That's what you're trying to understand. You need to, when you're working on these programs, on that, when you're working the big programs, very important websites, it will be very essential now to really choose an algorithm when you're writing an algorithm for maybe scrolling through charts, maybe an algorithm to scroll through a database of users. You might really need a proper algorithm to work with at that point in time. Let us begin with time complexity. Now, what is time complexity? Simply put, it is the amount of time an algorithm takes as a function of input size shown as n. For those who have seen time and space complexity being denoted all around, if you have done any unit among it or just seen it through your programming journey, you have seen n being used, basically every single, most of those, okay, all but one of those algorithms, of those big O notation. They're called big O notation. Don't tell we'll cover it so you can understand what that means. And we do consider that n is just input size. It's just the amount of data being put in, whether large or small. That's just what n is. Now, the key idea is simple. Large inputs take more time. And that's why we are saying that you need to write efficient algorithms that will take the minimum amount of time, space, and all that. And now, one thing to understand about time complexity is that it's not really measured in time. You don't measure it in seconds, you measure it in steps. We just care about the number of operations so that you don't go through a roller coaster of trying to do things, but we just want the number of operations to be minimal. We don't care about the time or minutes. If trust me, if the number of operations are minimal because they happen very quickly, obviously it's going to take less time. So don't confuse yourself too much, but you have to understand that we do measure it in steps, not in like minutes or seconds. Like just basically the steps is like just the steps of doing a task. That is it. Like I don't declare a variable. Maybe you loop through a list. Those are steps. Now that's what you care about, and we want them to have as minimal steps as possible. Now let's look at common time complexities. Now, as I said, Bigo notation, you'll see it everywhere. And I will still, I want to cover this right now. I will explain it and we'll still go over the Bigo notation again in the end. But I believe you can start here at the moment. So we have this, I've chosen the four main ones. There are very many of these times, but I've chosen the four main ones which you're going to encounter. They're the primary ones. I'm going to uncover these Bigo notations, these time complexities along the way. So the first one is O1, constant time. Basically, what it means is that the time stays the same regardless of input size. As you can see, it's O1. I told you that some of them which just don't choose the n, the input value, because it does not matter what the size of input is. So it really doesn't have n because, it's like n power 0 because it does not matter. So it's just O1, O1. Basically, if you're checking like a number, if you have brought a function to check if a number is even, it happens instantaneously. No matter if you drop a lot of numbers, it's just going to be the same. Basically, what happens is it does not matter what the input size is. What matters is it's just constant time, and you're going to encounter this a lot more because you're doing it constantly. Maybe declaring variables, simple functions, and maybe just print something. You're going to encounter this constantly, constant time. So this, I guess, that's why I chose to start with it. But now let's go into a bit depth there. The more things that when you're writing algorithms themselves, you're going to encounter a lot more. We have linear time, O of n. And for those who know math, you can guess what this means. We have an n there, and the n is the input size. So basically, time increases in direct proportional to input size, obviously. Because if you can see in that function, O(n), if n increases, obviously the number will obviously be larger. And luckily, because there are no other things in just the single n, it will be proportional. Because n is not changing, n is not being altered. It is always rising as n is also increasing, time is also increasing equally at the same rate. An example of that is finding item in an unsorted list. If you remember, we said linear search and all that, how they function. It's basically they function in linear time, especially when you're just finding something in maybe an unsorted list. You are starting from the start in linear search, the first one, the second one, the third one, going onwards to the end. And as you can guess, in such a scenario, obviously, if you have like 1,000 elements in that list, it's going to take like 1,000 steps. If you maybe the thing you're looking for is at the end. You see what I mean? It basically increases proportional to input size. Now the next thing is quadratic time, n squared. And now this is a bit different, obviously. Now time grows as the square of the input size. Basically, as n increases, now time increases now as a square of it, like n times n, basically. And this one is an example of it is when you're comparing pairs in a list. Like you can see the nested groups and all that. And if you have seen a functions you have written as you are writing, as you are working on search and sort algorithms, you saw in you are looking for I and then for j immediately nested inside the I loop. That is an example of it where you are comparing a lot over and over again, two different digits maybe in a list. And if you remember, like in sorting, as we did in binary search, as you are breaking the list into small parts and comparing and mashing, that works at a quadratic time. And then finally, we have logarithmic time. Time grows slower compared to input size. Now, this is another thing. Logarithmic time, if for those who know math, as you can see these four time complexities listed here, you can guess that obviously O1 is more likely the fastest. But look at here, we have log n. For those who remember mathematics in high school, you know that log n is obviously a very small number. When you look for the logarithmic value of a number, it's usually most of the time can even be lower than number, or it can even be in the decimal side lower than 1. So logarithmic time is basically among the slowest, the best. Like the best algorithms will most likely work with logarithmic time. And that's why you see the example is binary search. If you remember, I said binary search is the reason it is the primary, it is the fastest, it is the best whenever you are working with you're working with large data sets. This is the reason it works with logarithmic time, as it basically time just goes slower. No matter if you increase, basically no matter how much you increase, time will gradually grow. If you see I should have probably provided the graphs for these time complexities. You'll actually notice logarithmic time, it is slowly edging upwards, not as fast. Even if it's growing to a million inputs a second, it is still growing maybe at 10 inputs a second. That's what I mean. Logarithmic time is very quickly, because no matter how much you add in, time is growing slowly. Now, let's now check out that is a 10 complexity for us. And yeah, as we move along, don't worry. I hope you are going to listen to this, because as we move along, I will be coming back a lot to these complexities as we are writing algorithms for sorting, maybe linked lists and all that. So I'll come back to this. So note to self, or maybe you can come back to the video. I will provide it, and you can see. You can follow along as we continue the next classes. But now we cover space complexity. Now, space complexity in itself, it's not that common. Most of the time, it is calculated as time complexity. That's what you'll see mainly. Even in our units, you can see that time complexity is what they focus on, not so much for space complexity. But it is good to know it. You don't want to write an algorithm that literally takes an entire RAM. As you see, the application might get us somewhere, and you start to run them, and they take the entire RAM for something that is very small. You want to avoid that. You want an algorithm that can run with the minimum space, with the minimum memory, and still achieve a perfect or equivalent result. Now, space complexity, again, it is the amount of memory an algorithm uses as a function of input size. Leave your two. It's the same as before. You just calculate it as a function of input size, and you ensure that through this input, we still achieve minimum memory as possible. And now what is included here, we need the input data, the data you're processing, temporary variables, extra space, which is extra space used during processing, and output data, the results of the algorithm. These all are included when you say the amount of memory, because all this will be used as you're writing functions. Probably the function will take some input. It might have, like, if you're working where you're switching variables, you might use temporary variables, temp. If you use temp, you can use them. So it takes a space which is used for processing, obviously. And you have output data, the result of the program. All these are they take a bit of memory, and you want to ensure that your function balances them well enough to ensure minimal memory of working. And don't know. Okay, now there we have now common space complexities. I'm only covering 3 of them. It's not because it's not a big thing to worry about. But again, constant space, as constant time was, it uses same amount of memory regardless of input size. It's the same theory. Again, as it is equivalent. Basically, no matter how much, even if you have a million inputs to be entered in, it will still use the same amount of memory. Constant space. Maybe you're swapping 2 variables, as we said, you're using temporary and all that. It will always use the same amount of space, because in the end you are remaining with 2 variables. It's just ending up in the same place. Then you have linear space, ON, as again linear. It increases proportionally to input size. That is it. Linear space is like linear time. Memory, if you increase maybe 1,000 elements, it's just going to gradually increase to 1,000 times, like 1,000 spaces, like all that basically just increases proportionally to input size, as we said, in linear time. Like storing elements in a list, storing all elements of a list in another list. You can see you are literally creating more space of the same equivalent value of all the input size that you have taken. That's just linear space. And then you have quadratic space, which is memory usage grows with the square of input size. The same as the time complexity, now memory is growing by the square of input size. Now here is maybe creating a 2D matrix when you're working with Python and all that. You're going to cover it, but quadratic space, it's only going to see it occasionally. Right now, the reason I've chosen 3 only for space complexities is because in space complexities, most of the time it will be linear. And like most others, you can see they vary here and there. Most of the time, when you're working with algorithms, the one you're going to meet most is the linear. But quadratic still exists. Like I've said, 2D matrices, maybe you want to do that. Constant space still exists, again, because maybe you're swapping variables in your program. So yeah, those two first are constant and linear, you'll see more often. Here's where you can see the constant one is more common in space complexity than time complexity. And those two are very common. And quadratic is still there, it's still seen here and there. You might even encounter it a lot more when you're working on more complex applications, but that is it. Now you have covered time complexity, which is the more important, and also space complexity. And you know that you have to save time and you have to save space. And you have seen this zero, this big O here, and some brackets and some numbers within the brackets. Now let's understand what this is. This is called the big O notation, where you have seen us use the O and you see a bracket and some digits inside. That's just big O notation. It is a way to describe worst case scenarios of an algorithm. You always see when you're working with all these, you're going to see the best case and worst case. Like a best case is maybe something is close. Like let's look at linear search. Now, linear search best case of itself is basically now you have a list, and the thing you're searching for is literally at the start of the list. That is the best case. The worst case, because it's linear, you're starting from the start to the end. Now, the worst case is now the thing you're searching is at the end of the list. That now is what we say worst case. You want to see what's the worst case, because if your worst case is good, then definitely your best case is better, and any other situation will always be better. That's why you mainly concentrate on the worst case, because even if something can have the best case, like that's the linear search, the best case, if it's at the first, it's one, it's just immediate. But if it's at the last, it will take years. That's why we care about the worst case when you're considering algorithms. Now, what do? They help us compare algorithms' performance as input grows. And now we need to understand the hierarchy. As I said, for those people who know maths, you can guess. Obviously, constant time will be the least. Like, it's just immediate. No matter how much it increases, it does not change time. So, obvious constant will be there. Logarithmic, as I said, it is. Now you're going to see it more often in time complexities. Now, logarithmic time is basically now the second best. And you're going to see it a lot, especially in binary search, maybe even merge sort and all that. Then you have, now we have linear time, when. And then there are all the others. There are many of them, and obviously the most fastest is obviously this, because it's a what's the name of that? I've forgotten. But it increases indefinitely. It can go on. Basically, if you see like 2 factorial, basically the factorial version, like 2 factorial is easy, but look at 10 factorial, it can be as big as a million, as a million and all that. Basically, the factorial time is always the slowest, and the constant time is always the fastest. And now I did say I would come back to this table for the sorting algorithms class that we did, so that you can try and see where each applies. Now you remember we covered bubble, quick, and merge sort, right? And we said that merge sort is the best and the one you should use when you are working big applications, the one you are going to most of the time use. And now you can see why. Now we said clearly that bubble sort, if it's at the first, it will be quite fast because it's and it's a linear time because it's just there. At the best time itakuja unaipata ama iko karibu hapo mbele, you just find it immediately. If it's just close by, you're just going to find it immediately. But now look at the worst case. It's n squared because it will take a while. It is so, like, imagine a million, you have a million input values that you want to search from, and the last digit is at the end. Obviously it's going to take a very long time before you get there, because if you're using something like bubble sort, you're just going trying to sort, you sort again over and over repetitively up to the end. You can see it will take a very long time. Then you have quick sort. Now quick sort, it's a bit better because for the best time it is n log n. Is it a bit slower than O log O n than constant time? Yes, it's a bit so, but in the end, how should I put this? It is still good enough because time complexity in itself, at the worst case, you can say it stays the same as bubble sort, because quicksort is a lot of steps are involved in quicksort. Yes, it is okay and can work, but due to its lack of stability and all that, it ends up being kind of worthless. That's why I covered. I told you, quicksort, you most likely never use it, but it's good to know it. You're going to use it. Okay, you might even use it occasionally when you are learning. But in the end, I'll just tell you to go to the last one, which is merge sort. Now look at the merge sort. It maintains a time complexity from the best to the worst case. No matter what scenario, its time complexity will never change. It will maintain n log n from start to end, no matter the amount of size, no matter what, it will always maintain time. Then that sounds like constant time, but okay, no, it's not. But in the end, that's why people choose merge sort. Slow time for best, but the same slow time for worst. Because in the end, if you remember merge sort, you are splitting in the middle. No matter if it's sorted completely or not unsorted, you're going to start at the middle again, split it into the separate lists and combine them later, no matter how it was, because the time will always be the same. And actually, because that state takes a minimal time, which is n log n, not the slowest, but still works, it is best. And also, as I said, it maintains the stability of the list. Does not really matter if you have repetitive digits, it won't really matter. It will still include them there, so on and so forth. And now, as we cover the next class, you can see even much sort of, we said it is used in linked lists and large data. We will have to come back to much sort again, because implementing it in a linked list is a bit more complex than just implementing it over just a normal list. So we will come back to it and understand and cover again the time complexity which is involved in those algorithms. So now, I hope that was well. It's a very small class, as I told you. I told you it won't take that long. It has literally just taken over 20 minutes, just over 20 minutes, like 20, 21 minutes. Very simple, very fast class. But don't worry, if you're not completely understood and you want to see it in applications, from this class onwards, anytime I write an algorithm, I will try to explain each step and tell you what time complexity exists in each case. And for every function, for everything we write, I will come back to complexity. But I'll only really cover time complexity, because that's the biggest thing that we really want to look into. But space complexity is as simple as ensuring that you don't leave variables running around. You get maybe rid of memory and all that. Those are things that you'll end up just finding along the way. But time complexity is something that we really want to understand when you are writing the functions, when you are writing these algorithms, or so on and so forth. So whenever I cover any algorithm, maybe it's an algorithm for sorting a linked list, maybe the algorithm itself will be a linked list. I can even show you how that works, even that it does not really matter much. But in the end, whenever I will be showing an algorithm, I will always cover its time complexity, tell you its best and worst case, and explain why I've chosen I am indicating those specific time complexities. Okay then. Now I do believe that is it. Actually, I do believe that is it. A very short, very intuitive class about the simplicity of these time complexities. And now that I've covered that, I do believe we can now continue straight onwards to data structures. We will obviously start at a linked list. That is the best place to start, and the one you're going to encounter a lot more in your programming journeys. And we'll start at linked list, and we'll see the way forward from then on. We'll look at the stacks, heaps, all those trees. Even we'll cover them eventually. These classes will be happening every 2 weeks, so it will take a while before we get to the end. But in the end, what matters is that we cover everything. Mohammed, I can see your hand is up. I do believe you might have a question. Ask away.
Yes, I have a question. Can you please show a random code and find the time complexity and space complexity of that code?
Yeah.
Can you please show a random code of any algorithm, sorting algorithm, and then find the time complexity and space complexity of that code?
Okay then. So for the code, as I said, I will show you. Okay, I will show you the time side. The space side is a bit more challenging to calculate. It's just easier to observe the time complexity side. So give me one moment as I look for one of my code to show you how it works. Give me one moment. I will look for a simple code. There has to be some code somewhere here. There has to be some code somewhere here. Give me one moment. I do hope you can wait. And I think the best I can show is probably linear time. Or maybe I can show logarithmic time. Okay, let me just show linear time. Linear time will be one you're going to encounter a lot. So let me show linear time. Give me a moment if I can open VS Code with this. Give me one moment. One moment. Give me one moment. One moment. Give me one moment. It's taking forever. Okay, let me share this screen with you. Let me share this screen with you so that we can understand what this entails. Give me one moment. What's happening here? Let me share with this. Okay, here. Share this window. Share. Okay, there it is. This is just a code snippet. This is just a code snippet that I have a very simple thing for linear time. Now I can show you exactly what it means. Now we said linear time is basically the time increases relative to proportionally to the amount of input is put in. And here we have a simple function. That's what it does. It basically comes here, okay, as a function, linear time example, takes some numbers, which is here, these nums, whatever, it takes a list of numbers. And then finally, we are going to add them all into total and have it. Basically, just finding the sum of these numbers. Now let's sit here and ask ourselves how this works. So now let's say we have these 5 digits here, and we want to figure out what time complexity it uses. Well, simply put, step one, we are now inputting numbers here, and we're going to iterate repeatedly over each number in the list, then add each number into total. What does that mean? Simply put, is that we are now moving from one number to the next, the next, the next. That means the more you increase numbers, the more you have to go again to the next number, to the next number, to the next number, over and over again. So now, if maybe you have, like, this could take like 5 steps only, like just the first one, the second one, the third one, fourth one. Those are just 5 steps. And now, if you add, the more we add here, no, that's 7 steps. No, that's 8 steps. No, that's 9 steps. Goes on and so forth. That's just is. Linear time, you're going to see it constantly because you're going to see functions like this in almost everyone's code, no matter which way it is. And basically, that's what linear time is. It's just increments slowly onwards and so forth. And I know, Mohammed, you're going to ask about the others. Don't worry, I'm going to, for the others, it's best I show them in a proper practice, like using them in a complete project. That's why I've said that in the next classes, you're going to really get, as we are doing the merge sort and all that, you're going to see. Like, that's why I've just showed you the linear time, because I doubt you're going to meet it that much when you're working the program. I try to avoid it as much as I can. But the logarithmic time, we are going to really see it, especially with the merge sort. And when we cover again binary search and all that, we are really going to see how this applies. Don't worry, the class will happen as soon as I am able to, and we can even cover that we're going to cover it in detail. As I've said, that you'll be able to attend the next classes and so forth. You're going to see how we are going to implement these algorithms. We calculate it slowly from step by step, and then so forth. You are going to understand it. Okay, Mohammed?
Okay, sir, that's fine.
Okay, then. Anyone else with a question before we end the class? Anyone else with a question before we end the class? Anyone with a question? And for those who have gotten late, don't worry, I will I've recorded this class, and we will ensure that I provide both the recording and the transcript will be accessible for anyone who asks me through whatever platform you got the link. You can ask me. And so yeah, is that. Okay, now I do believe there's no one else with a question. So see you in the next class. And I do hope you've been able to try and understand. If you're not, you can go over it, and you can also check more videos online. As I say, mine is not just enough. It's good enough that I've showed you this, but now you can go online, go to YouTube, learn them, even get ahead and understand how to even calculate space complexity to detail if you want. That's all up to you. But we will just be covering space complexity because that's the biggest and most important one, and the one you're going to really be able to see and view mostly through our functions and programs. Thank you for attending the class, and I do hope to see you in the next one.